Okay, these are some notes on section 7.1, and I'm just going to kind of use the notes that I've written. Hopefully you can see all these. If you have any questions, please email me. Anything that I miss or anything you don't understand, please let me know. Please read the section on page 379 up on the top, Chapter 7 overview. They do talk about the process of integrating to find values, displacements, especially displacements that we're talking about. So you kind of see that and how that there's historical significance to what we're doing. And here's just a kind of an idea. Displacement, remember we talked about displacement before, and that would be, if we talked about this, we go look over here, that was our position. If we were talking about the displacement over an interval A and B, that would be our position at B minus the position at A, or in other words, the position that we end up with minus the position where we started. That's our displacement. That's how far we've moved. So we're going to be looking at this now rather than from the position function like we did back in chapter 3. We're going to be looking at it in terms of the velocity function, realizing that the derivative of the position function is the velocity function. And the velocity function will be in like feet per second or miles per hour. And if we want the displacement, that would be the rate of change times the time. In other words, if we're going 2 feet per second times 5 seconds, we've gone 2 feet per second times 5 seconds is like 10 feet. And the seconds cancel. So that gives you kind of a model of what's happening. So the velocity times the change in time gives you the displacement. Okay, the rate of change times the time. And we can model that by this little increment here. This would be if we were drawing about these little rectangles, we have a curve, and we're going to add up all these little rectangles, and to try to get an idea of what the area under the curve, this might be this might be the altitude of that rectangle, and this would be the base. And this would be just some point in that kth rectangle. So we can break this up into little increments. And this is the rate of change times the time. So this would be the displacement under a velocity curve. Now, if this value is negative, that means we're moving left. If the value is positive, it means we're moving right. So all those will be taken into consideration when we're adding up all these little increments, and that's going to be what we call the displacement. So this is the sum of very small position changes. It may be positive or negative, right or left, as I sit over here. And we would sum all these up over an interval AB as the sum of all these displacements. This would be the base of all these little rectangles or whatever figures we're going to use. And this would be the height. If we're using rectangles, we're going to do that. Base times height will give us the area, and we're going to sum up all those areas. Each area will represent a small position change, because that's going to be, again, rate of change times time. So it's kind of like what they're talking about, and we know how to change this concept, this Riemann sum concept over this interval, into an integral. So that would be the integral from a to b of f of t dt. Now, if we use our fundamental theorem of calculus in the second part, remember we would just evaluate this at the antiderivative, so you can think about that. Remember, the antiderivative of v of t is s of t. Remember, the derivative of the position function is the velocity. So the antiderivative of the velocity is the position function. So this would be like my capital F of b minus capital F of a. And again, that does give me the displacement in terms of the position function. But now we're looking at this all in terms of the velocity function. And again, this is very similar to what we talked about in chapter 3. Our new position is the initial position plus the displacement. Okay. Then they also talk about the total distance traveled. And the total distance traveled, whether we're going left or right, we're traveling. So that if you start at home and you go to school, then you come back, well, your displacement is 0 because you haven't gone any place, but you actually have traveled the distance. So the only thing is that the positive distance and the negative distance are the same, so they become 0. They add up to be 0 because the distance in one direction is positive and in the opposite direction is negative, so they cancel out. But you really have traveled something. So that's why we have to take the absolute value of the integral, because we're going to get the actual value. And this is kind of like area between the curve and the x-axis. If it's below, it's negative, and it's above, it's positive. But we actually do have area there. It's just, I would say, if it's above or below, the integral is negative or the integral is positive. So we have to check that out. So we have to be aware of what's going on. And again, we've talked about this. I'll just draw a little sketch over here. So if that's A and that's B, remember the area above and the area below, they might be the same, in which case the value of that integral would be negative, but the area between the curve would actually be this and then negative that, so we take the absolute value. So if we took the absolute value, it'd be like this. It would go back up there. So you'd actually have this much area between the curve and the x-axis. So there's a difference there. So we have to be aware of that. That's why we have to take the absolute value. So if we take the absolute value of the velocity function, then we're going to actually get the distance traveled. The actual distance traveled, not necessarily the displacement. Okay, so this will give you this displacement, and this will actually give you the actual distance traveled. Okay, so I hope that makes sense. All right, and then we'll go through the examples. I'll just be following the examples in the book, so you can kind of read along, and hopefully those will make sense. And then we've done enough homework problems, so you should get a good idea. So we'll stop now, and then we'll have another set of notes on the examples.